Good morning, everyone. Welcome to the second session of our Introduction to Quantum Machine Learning workshop. Today's session will be on the comparison of classical machine learning and quantum machine learning. I would like to remind you that all the sessions will be recorded. We express our gratitude to our instructor Barış Malcıoğlu for accepting our invitation. I will briefly introduce him before giving him the floor. Dr. Malcıoğlu received his bachelor, master's, and PhD degrees from Middle East Technical University Physics Department. He worked as a developer of the theoretical spectroscopy module from basic principles at Quantum Espresso at Sissa, Italy. After working at the physics department of the University of Liège, the materials department of Erlangen University and Erlangen University and the physics department of the University of Salzburg, he started working as a faculty member at metaphysics department in 2019. Dr. Malcıoğlu teaches undergraduate courses on quantum computing for scientists and machine learning with quantum computers. His main research areas are quantum artificial neural networks, computational spectroscopy, and functionalized circuits. So, welcome, Dr. Malcıoğlu.
Thank you very much for the nice introduction. So, good morning, everyone. So, first of all, this is today's schedule. For those of you who joined us a little bit earlier, I was sharing this slide in the, let me share it again. I was sharing this slide from my presentation. I have already uploaded all the things that I will talk about today, including this presentation, to my GitHub account. You can download it. I encourage you to do so. The exercises in those Jupyter books will not be graded or will not be checked. You can find the answers also in the GitHub if you want to check if your answers were correct. But if you can just, while I'm giving you an introduction to this topic, I would be very happy if you can just download the Jupyter notebook and try to run it with your own resources. So, a couple of weeks ago, maybe you have heard, there was this big announcement by IBM. So they released commercially the Condor, which has more than 1,000 qubits, and it is commercially available. It's already being set up in Spain, in Bilbao. So this is quite an important achievement. And as far as things are going, there is this law in silicon circuits. There is an equivalent for that for quantum computers. It's called Rose's law. So every 2 years, you will have double the number of qubits. So as the number of qubits are increasing, we are entering into an interesting era. If you are following Davos, people were talking about the transition, the impact of quantum computers to the economy. The biggest impact, the short-term impact, will be in cryptography. We will not talk about this, but let's talk about what this means for us. First of all, as the number of qubits, these are not logical qubits, so you have to distinguish between a physical qubit and a logical qubit. So the logical qubit is this perfect entity which you can do quantum information theory without dealing with noise. But with these physical qubits, what you can do is error mitigation. And when you have many qubits, this error mitigation becomes more feasible and easier. So as you increase the number of qubits in these kind of near intermediate scale noisy quantum computers, you get more and more viable things. So why people are so much interested in quantum computing? One way of looking at it is about complexity theory. If you know the complexity theory in classical traditional computing, it is slightly different in quantum computers. So what this practically means is that quantum computers can solve problems that are different than traditional computers. So traditional computers are really good with some problems. Quantum computers are really good with some computers, and they have an intersection around here where both of them are quite good. So people are concerned about cryptography because although most of the cryptography algorithms, the ansatz is practically unsolvable for a traditional computer, it is not necessarily so for a quantum computer. So this can really break the commerce in the current world. So this is not what I'm talking about. This is maybe what you are interested. So as you can see, the number of qubits are increasing twofold. They are increasing exponentially every 2 years. It is slightly faster than Moore's law. And there is this thing called quantum supremacy. So this quantum supremacy is actually a buzzword. So it means that there's this problem which quantum computer can do really well, but traditional computer is not so good at solving this problem. So when you have something like 100 qubits or so, you can find problems. Even the best computer in the world can solve this problem within a meaningful amount of time. So we are already past this, and we are around here, and this will become better and better. We are almost closing the NISQ era now. So we are entering this unknown era where, well, the applications of the quantum computers are open to discussion, let's say. And by the end of 2030 or 2035, then you will have these quantum computers that are quite good at solving, let's say, quantum problems. In any case, what can we use the quantum computers for the societal problems, for the problems that we have at the moment while we are in this intermediate step? Well, one thing is, let's say, ChatGPT. It's quite popular. So in Davos, one of the problems of these kind of large language models was put in front by Sam Altman. I mean, when you look at how much energy these models are using in order to be trained, I mean, this is a huge value, 62,000 megawatts hours. I mean, this is really something quite important, quite significant. And in order to go beyond it, I mean, in order to go from ChatGPT 3 to ChatGPT 4, you need something like 40 times more energy. So in order to go to ChatGPT 5, who knows how many times more energy you will require. So they are discussing about using nuclear reactors and fusion reactors and whatever. As you can see, the scaling of these large language models is not that good in terms of energy. And when you look at it, when you try to compare a quantum computer with a traditional computer for doing similar tasks, it is a little bit of an estimate, but you have something like 100 times more efficiency in IBM's Condor. And as the number of qubits are increasing, the scaling will be much more favorable in the quantum computers. So for bigger quantum computers, you will need even less energy compared to a traditional computer that can do the same thing. So another thing is that these large language models, these current trend in AI is, they are extremely data hungry. So, I mean, you started with 40 gigabytes for GPT-3, you needed something like 570 gigabytes of data, and they don't even announce how much data was used for GPT-4. And this is actually quite a big problem because, for example, there are legislations. The European Union is not happy how this much data is being collected and analyzed. So OpenAI has some trouble with the new AI laws in European Union. And another thing is that, for example, imagine you are a car company trying to implement your own version of autonomous driving. It is impossible to compete with Tesla because Tesla has been collecting data for 10 years now. So how do you, I mean, this data is not open. So how do you train a model when you don't have that much data that will be as good as the Tesla's models or whatever? So this is a big problem. So quantum computing is, in some cases, for generative models, is a very good solution for that, because you can find structure in data much more effectively if you embed it using quantum machine learning things. If you are interested, you can go and check this article out. So at the moment, what is happening? So quantum computers are used as if they are like graphical processing units. These things are called quantum processing units, and they are working together hand in hand with traditional HPCs. Traditional HPCs work in mitigating the error, analyzing data, and programming these quantum processor units. They complement each other. So if you are looking at this from the complexity class perspective, so they are complementing their complexity classes. So you have a wider spectrum of problems that you can solve. Okay, so before we start the lecture, just introduction to some jargon. There are various ways of constructing quantum computers. Today we will be using IBM Qiskit, so it is more intended for superconducting circuits, but especially for space applications, photonic systems are much more interesting because they are much more resilient to space radiation, this charge state problems. And you can also embed them directly to the communication hardware, so you can just do computation simultaneously with communication. So this is quite interesting. There are also some other applications like trapped ions. They are quite interesting because you can do some interesting quantum sensing experiments with them as well, and neutral atoms. In any case, just for you to know, today I will be showing you what is called the circuit model. We will be focusing on the circuit model, but the circuit model is not the only way to do computation in a quantum computer. So you can have different models to do quantum information theory, quantum computation with a quantum computer. So these are some examples, and these are the references. You can go and check this out. But in any case, for this tutorial, we will be focusing on the circuit model. So the circuit model is read like a music note. So you start from left to right. So these guys here are qubits. So these lines are qubit lines. So what happens is that you have an initial state, you reset it, you put it into whatever quantum state, or this zero means that you have reset it, and you apply operations on them. So this is a single qubit operation. It only acts on a single line, and this is a 2-qubit CNOT gate, so it acts on 2 qubits simultaneously. So you do these kind of operations, and when the time comes, you do measurements. So when you measure, the state of the system collapses, and these are the classical parts. You send it to a classical readout circuit, you send it to the computer, and you do analysis. What you can do is that you can also have these gates that can be controlled by a classical computer. Like if you are into photonics, you can just think of it as a motorized polarizing plate or whatever. And this is what we will use for parametric circuits and in order to do quantum machine learning. So if you really want to harvest the quantum information theory, the effects in quantum in order to gain some advantage over classical machine learning, you have to know about the postulates of quantum mechanics. I will not go into details, but you can find these in the slides, and there is this very nice book. You can also go and check this out. I also have I mean, there are many courses around for quantum computing. You can go and watch them and learn about these. So the thing that you are trying to optimize, trying to add to traditional computing is these three fields. So you want to, let's say, take advantage of linear superposition. So you are not dealing with just a bit. So this qubits can be in a superposition state of 0 and 1. And if you exploit that, then you will have a huge advantage. And the second thing is quantum parallelism. So you can use this inherent parallelism in quantum in order to gain a lot of energy advantage and let's say speed advantage and entanglement. So this is what enables you to discover structure in the data and do much more with much less. Okay, so these are the slides that I wanted to talk about. It is just a motivational speech, more or less. So I hope in the meantime you were able to download the Jupyter notebook so we can start working on it. So everyone, I hope, is ready to go with the Jupyter notebook. Okay, so let's start. So I am a physicist, so I always start with kind of establishing a baseline between the two nomenclatures. So if you are coming from machine learning, if you are an engineer, and if you are coming from natural sciences, then this communication is not straightforward. So jargon between two fields can be a little bit different. So this lecture is intended for those of you who already know concepts in machine learning, but let's say get an introduction about QPUs, how to integrate quantum processor units to your workflows. The things that you will see as examples in these notebooks are not necessarily things with significant quantum advantage. So it is just to establish a communication between the two groups. If you are interested in things that really have quantum advantage over traditional AI models, I recommend you to go and check my GitHub page. I have this course 710, which talks about some of the models which really have quantum advantage over traditional models. So let's start. So in machine learning, we have supervised learning tasks. So we label the data. So as a physicist, what I see this machine learning workflow is it consists of two steps. One of them is the data science step, where you prepare your data for a model, and then you have the models that can analyze that data. So the supervised learning is about labeling the data. So you just label these guys as crosses, label these guys as circles, and you try to find a model that will separate these data into two. The unsupervised learning part is that you don't label the data, you just feed the data with some kind of encoding, and you ask your model to find a structure within it. And you have also what is called a reinforcement learning, where you are training the model as if it is a child. You are giving it a reward for completing a task. So this is for example, how you teach a traditional model how to play Pac-Man or that kind of stuff. So for quantum machine learning, now there is this distinction. So as I told you, in my point of view, there are two steps in machine learning. One of them is the data science part, and the second part is the model part. So your data science part, your data can be classical or it can be quantum. And also your model can be a classical or a quantum model. So this means that it is like a square. So you have something like classical data, classical model. You have classical data, quantum model. You have quantum data, classical model, and you have quantum data and quantum model. So it is like a matrix like this. So this classical data, classical computer, it is what the traditional models are. So you can just do this with traditional AI techniques. But if you want to use quantum information theory for this task, classical data, classical model task, there are some advantages because, for example, NVIDIA provides these libraries that will handle the parallelism, modal parallelism, and let's say acceleration for you. If you can fit your model, traditional model, translate your traditional model into a language that quantum information theory does, then parallelism of the model, you can use something like hundreds of GPUs, and you can accelerate this by using tricks of sparse matrices and tensors and whatever quite easily. So this is still interesting for us. So if you have quantum data and classical models, this is popular. For example, there are these models in scientific community that try to understand what is going on in a quantum system using traditional machine learning models. So this is quite interesting as well. AlphaFold, for example, can be considered as a model like this. When you have classical data and quantum computing, this is point of interest at the moment. What you are trying to do is to use quantum processor units in order to obtain some energy or speed advantage over classical traditional models. So this is what we are going to talk about today. This quantum data and quantum computing is something relatively academic at the moment. It is quite interesting. As a scientist, this is what I am most interested in. Well, it is at its very much infancy. So you need some components like nice working QRAM quantum memory in order to achieve something significant with this. So this is not there. In any case, today we will be talking about classical data and how to use quantum computers to do machine learning tasks on the classical data. So the magic ingredient in our quest to use quantum computers for machine learning tasks is parameterized quantum circuits. So these parameterized quantum circuits are something like this. So for some reason, it did not work. Let's see if it is working. Okay, so what this guy does is that it takes some qubits in whatever state. You can reset it or you can keep it, and it applies a gate that is controlled by a traditional computer. So this theta, this value is coming from a traditional computer, and this is applying an operator that is parameterized with this traditional data on this qubit. So similarly, this is a 2-qubit operation, and it is also being controlled by traditional circuits. So what is the thing that we are trying to achieve by these parameterized circuits? So one of the things that we are trying to achieve is to have these circuits as expressive as possible. What does expressive mean? By the way, this is our first exercise. While I'm talking, I encourage you to do this. So the answer is already in GitHub. If you don't know what the answer is, please try to code these circuits. You can just copy and paste from here in order to, let's say, conclude this task. And what we are trying to achieve is that this is, this is what we call a block sphere. So it's contains, it shows you in a handy form all the possible superposition states this qubit can have between 0 and 1. So the first circuit, as you can see, it is just putting our circuit into computation space, and it is just applying a simple rotation. So oh, what happens? And this simple rotation, as you can see, you can only reach these points in the block sphere. So all these other points you cannot access with that circuit. No matter what parameter you put in that circuit, these points that are along the sphere will be out of reach. On the other hand, the second circuit has a rotation in another axis. And as you can see, by controlling these two parameters, you can reach any point on the block sphere. So this second circuit is much more expressive. So you can just capture most of the Hilbert space, the available data that you have in your system. Of course, this gets more complicated if you have more than one qubits and if your system is entangled, but I hope you get the idea. So you want to have an expressive circuit, but at the same time, you don't want that many gates, because then you will have problems with the noise. The second thing is that I told you entangling is a huge resource for quantum computing. So if you are just using a circuit like this one, where you have only qubits that are hanging on their own, they are not interacting with other qubits, then a traditional computer is better for your model, because traditional computers don't suffer from the noise and they have a huge number of bits. But this is not something that much desirable when you are doing quantum computing. So you want to entangle these states in order to gain quantum advantage. One thing that you have to look out for is that the more gates you apply to a quantum circuit, the more noise you will have. So you are trying to construct circuits that do the same thing with least number of gates. And depending on which hardware you are using, not every gate is accessible to you. So they have to be approximated by many different types of gates. The transpiler, the thing that converts the circuit diagram into a language the particular architecture can understand, is called a transpiler. Transpiler does this automatically for you, but if you are, let's say, really trying to optimize a code, it is a good idea to understand how this transpiler works and do some of the optimization by hand, because for sure, if you understand what you are doing, you will always do a better job than an automatic transpiler. Okay, so in quantum machine learning, parameterized quantum circuits, you use them for two things. For data science, to encode data. So this is in quantum jargon is called data embedding. So to embed the data to quantum computer, you use parameterized quantum circuits, and then you use it in the quantum model in order to do machine learning, in order to construct your model. So you can just see this reference for how this kind of things work. So this is a quick example on how to use Qiskit circuit library primitives in order to embed some data. So this data encoding, this data embedding is a crucial part in your workflow. It will determine, your strategy, what you are trying to achieve is determined at this step. So the most easy to understand encoding is what is called basis encoding. So basis encoding is it's simply using qubits as if they were bits. So it is not a very effective way of using qubits. So this basis encoding is very qubit hungry. You have to have a lot of qubits, but you still can have some quantum advantage because you can just use quantum parallelism and you can do some tricks like phase kickback tricks or whatever in order to make computation much faster and much more energy efficient. So what you do is that you code your data into a state by just encoding it as if this is a bit string. So this is an example of how you do this. One thing you have to be careful of is that in IBM systems, the convention is reversed. So IBM is a very old and traditional company. So they are using this reverse ordering for the representation of data. So just be aware that if you are using IBM machines, there is this additional thing to consider when you are encoding data. Okay, the second one is amplitude encoding. So what you are trying to do here is that you just want to encode your data as the amplitude of the eigenvectors of a quantum state. So what this achieves is that it is actually much more efficient in coding the data. So you are not using the qubits as bit strings anymore. So you can use the superpositions between the qubits in order to describe your eigenvectors, and then you can just put your data into the amplitude. So this is much more qubit efficient. And here in this example, you can see how the scales. Please try this. And another thing is angle encoding. So this is another way of using the fact that qubits are not just 0 and 1, but it is a superposition. You can just rotate the qubits in order to encode your data. And there is this arbitrary encoding, which we will use today, where you just use a parametric circuit in order to encode your data. So a common example is this efficient SU2 circuit. So for example, in order to embed 12 features using efficient SU2, you will only require 3 qubits. So please go and check this out. Okay, so for those of you who already know the old Qiskit, things have changed. So this is why I was asking you to install a newer version of Qiskit. So the language of Qiskit changed significantly over time. So in the new language, what you have is what is called primitives. So these primitives are core functions that make it easier to build modular algorithms. Well, in practice, what it says is that, okay, we are no longer interested in providing services only for natural sciences. We want to expand our sphere to traditional computing tasks. So they are finding a middle ground between computational science and natural science. So what they have come up with is this two primitives. One of them is sampler and the second one is estimator. So estimator is what you know from natural sciences. You just calculate an expectation value, which is guaranteed to be a real number, and you do your computation with this. Sampler is something interesting. So you just get a quasi-probability distribution from the input circuit. This is quite handy for machine learning tasks, but it doesn't necessarily make sense in a natural science perspective. So the estimator primitive is used like this. You start with a random circuit like this, and you define an observable. This is something, if you have taken quantum physics courses, you know what an observable is. So this is just an operation that collapses the wave function and gives you a real world observable value, and then you get your result. So you just estimate with this observable. At this stage, you have to choose whether you are going to use a simulator or a real computer. You can learn how to do this if you are already using the IBM's notebooks at the moment. You can just use the quantum computer to do this. It's a very small one. It will not cost you. So please do this and let me know in the chat if you have problems following this. Okay, so another thing about, as I told you, you can just obtain quasi probability distributions from Qiskit now. So you don't need to define an observable. What is interesting in the context of machine learning is that there is this circuit called real amplitudes. So this real amplitudes is guaranteed to give you real values, which is what you are looking for in traditional machine learning models. And if you just use real amplitude circuits and you use this estimator plus, so what you can do is that you can just skip the observable step. Okay, let's make a comparison between quantum versus classical neural networks for tasks that are intended for traditional machine learning tasks. So if you are coming from the machine learning, quantum neural networks are algorithmic models that can be trained to find patterns in data similar manner to their classical counterparts. You are just using a quantum computer, but you don't need to know the details. It is already, let's say, there for you. This Qiskit machine learning library contains lots of models that you don't need to know the details. You can just approach it in a, I don't know, cooking-like approach. You can just mix them, match them, quantum convolutional, for example, in order to do add some quantum spice to your model. You can replace your convolutional network with quantum convolutional network. Why not? Just to see what is going on. This doesn't mean that you need to know what is going on in the quantum circuit. It's just implemented for you. And if you are from the quantum computing perspective, quantum neural networks are quantum algorithms based on parameterized quantum circuits. And then you do the training not on the quantum computer, but in the classical computer, and it looks like this. So you have this task of data loading, embedding your data into the quantum computer. So you start from reset states, and you want to input your data so that the ansatz will be able to process it. And then you do the processing, and then you do the measurement. This measurement is also quite an important task because whenever you do a measurement in a quantum system, the wave function collapses, so you have to restart all the experiment once more. So this is implemented in Qiskit machine learning library as like this. So you have this big parent class, which is called neural network, and you have these two subtypes. So this estimator quantum neural network is a network that is based on observables, and the sampler QNN that is based on sorry, quasi-probability distributions that you directly sample from the state. So let's see how you can implement this. So tomorrow I will show you how to make this work in a hybrid manner, how to add some quantum spice to traditional network methods. But let's see how we can just do typical machine learning tasks in our system. So let's start with single qubit case. So this, you are just putting a qubit into a computation state, and you are just I mean, this is the simplest quantum neural network that you can do. This block, this Y rotation gate, is embedding your data. Whatever you want to embed will be handled at this rotation gate, and you can control this input one in order to choose how your data is embedded. And this is your model. So it is a training model. There is this famous example called single qubit classifier. I will not talk about this. This is not what I want to do today, but if you are interested in this, please go and search for single qubit classifier. You can do classification tasks with only a single qubit. So this is your model. Then you do the measurements and you measure it. So this is how that is implemented. And then you have the sampler quantum neural network. You have to be a little bit careful with this. So the shape is not automatically determined for you. These are technical details, but in order to use sampler QNN, you have to be extra careful about your data, whether you have complex values or not, and how to deal with errors is another problem that you will encounter often in sampler QNN, but it is very fast and very easy to implement. Okay, so the forward pass is actually, let's say, running the circuit once it is trained, or in order to understand I mean, you have been to the standard PyTorch workflow. So what you are trying to do is that you are trying to train this guy as if it is a child. So if you say, no, this is wrong, this is not enough, you have to be able to tell how wrong it is. You have to quantify how wrong this thing is doing according to your target. So this forward pass will give you an output that you will use for a training algorithm that will tell the model how to update itself. So this forward pass is just running the model and getting the results. So these are the examples on how to do it with estimator and how to do it with sampler. And this is a non-batched forward pass. I hope you remember what a batch is from previous lectures. And a batched forward pass using both estimator and sampler QNN. Now, what is interesting is the backward pass. So this is essentially the training of the quantum neural network. So you need to update the weights, the parameters in your parameterized quantum circuit in order to get the result you want. So if you want to use the nifty features of Qiskit, you need to use this thing called torch connector. So Qiskit is very well integrated with torch, and it is using the workflow of torch in order to do machine learning tasks. So the backward pass is practically handled by the gradient, let's say, optimization algorithms that are coming from, let's say, torch. So these two examples are giving you how to do a backward pass, how to do a training in the quantum neural circuit. So quantum neural network, please go and check this out. Okay, now today's first task is to talk about the most basic, hello world of quantum machine learning. Machine learning in quantum machine learning. So classifier is typically the first thing people are taught when they are, let's say, when they are initiating the machine learning. So this classification task is quite simple. So this part is generating some random data. You have these green circles and you have these blue circles. So what you are trying to find is a line like this that separates these two data. So what you are going to do is that it will start with a random line like this. You will tell the model how wrong it is, and it will update the line so that it will have a separation that looks like this. You don't have a huge or any significant quantum advantage, but it is a very pedantic way of introducing the quantum machine learning, so please bear with me. So what you do is that, as you can see, you just need to embed your data. So we are using the ZZ feature map for embedding the data. And then we have this real amplitudes ansatz for our model. So you do a forward pass, and then you obtain the data, and then you just put it into, the quantum Qiskit quantum neural networks optimizer. So it automatically chooses gradient descent algorithm for you, and it does a number of passes. And as you can see, it approaches the data. So what you are trying to do in machine learning is that you want to separate your data into a training and a test set. So the training set is what is used for these backward passes in order to train your data, and you want to see if your model is really learning or memorizing by exposing it to a test data set and see if it is really performing well. So as you can see, the model has sometimes some issues. This is because of the optimizer. So in this do-it-yourself, you can use different optimizer methods in QNN. So while I'm talking with the next part, I encourage you to modify the circuit above, just copy and paste it. But instead of using the standard optimizer, just choose a different optimizer and see if it is improving. So you can also do this with sampler QNN. Sampler QNN has a different set of things to deal with. So the result is slightly worse, but it has some advantages on different contexts. People use this classifiers for some tasks. You can go and search for the uses of it. They are not as interesting as the classical traditional models, but still they are interesting enough to have a special name attached to it. So the variational quantum classifier, when you encounter something like this, corresponds to a sampler quantum neural network that uses cross entropy loss function, and it expects labels given in one hot encoded format, and it will give out predictions in that format. So this is how you construct a variational quantum classifier. It works relatively well. And the advantages of these kind of models is that when you have a lot of data, it has some advantages mentioned in the previous paper. Please go and check this out. So you can also do multiple classes with a variational quantum classifier. You can have different types of data in your system, and then you can do a classification task with this data. The advantage of these kind of classifiers when you have more than 2 or 3 types of data is that practically by using quantum information theory, you are taking this data into a higher dimension. So think, it is not possible to find a straight line between these realms if you are thinking it in 2D space, but imagine you are lifting these dots up. So you have another dimension to play with. So by adjusting how much you are lifting these guys from the ground plane, you can find a straight plane in this time, since we are talking in 3 dimensions. Now, instead of a line, we have to talk about a plane. You can find a straight plane that differentiates between this data. So if you have more types of data, then this kind of going quantum might provide some advantage. Okay, let's continue with the traditional machine learning teaching workflow. The second thing typically students are exposed to is regression. So regression is just fitting the data. So you have a bunch of data points and you are trying to find a curve that fits this data as much as possible using a penalty function. So this is how you do regression with an estimator quantum neural network, and this is how it behaves, the objective function value against iteration. As you can see, for a regression task like this, the quantum model worked as good as the traditional model. I don't know if there is an advantage over the traditional model, because traditional model also works very, very well. But this is one of the things the quantum models are quite good at. So since again this is a significant task, and it is not straightforward to find something that is both practical and working. The particular combination of approaches that give you a very good workable result is called variational quantum regressor. It has this acronym like this. So it's a special variant of neural network regressor with an estimator. You need to use estimator QNN, and the loss function is fixed as well, L2 loss, and you minimize the mean square error. So this is, I mean, if you just use this combination, you end up with what is called a variational quantum regressor. Variational quantum regressors work quite well, so they are as good as the quantum models. So what I want you to do, if you are still interested with tomorrow's lessons, I will be talking about how to use real quantum computers by quantum error mitigation, how to deal with what is called a flat plateau problem, and how to use generative and autoencoder circuits. But before I will be able to talk about this effectively, you have to go through this network, go through this notebook, and do these exercises, at least be able to construct a regressor and classifier by yourself. If you can construct these by yourself, then it is, I think you will have a better time with tomorrow's lectures. You will have first-hand experiences with what can go wrong and what is better with a quantum computer. So we can talk about these in more details tomorrow. Okay, is there... Okay, so I see a question in the Q&A, maybe.
Yes, we have one question from one of our participants. Is there anything I can use to better familiarize with qubits and their properties?
So there are, I mean, in this lecture, I'm not, my task is not about talking about, oops, sorry, quantum computing in general, but Xanadu, this is a photonic supercomputing, quantum computing initiative. So Xanadu has a tutorial on quantum computing. So Xanadu, welcome to Xanadu. No? Okay, so the name was
Under the
Xanadu
page
Codebook.
cookbook.
Cookbook.
Another cookbook.
Yeah. So if you can follow these, I think this is one of the better ones that teach you about the properties of qubits and a little bit of quantum physics as well. But if you are not interested in quantum physics, but if you are interested just on, okay, how to embed this into my existing workflow without learning quantum physics is that IBM has also these quantum tutorials, Qiskit tutorials, that will teach you in a more technical point of view. So you can also go and check this out. Okay. But this is, I mean, going deep into details of quantum computing is not necessarily for our tasks. Okay, any other questions?
We have a question in chat box. What will be the advantages of using quantum neural networks?
So this is something I talked in the beginning. The immediate advantage at the moment is energy. First of all, instead of using the yearly energy consumption of 100,000 buildings, a typical building will have something like 6,000 megawatt hours per year, maybe. No, even less than that. So this is something like 100,000 household electricity just for training one of the GPT-4 passes. So they do it every 3 to 4 months. So instead of using this, you can use 100 times less energy in order to do tasks that are compatible, not for every task. And the second advantage is that you can learn more with less data. So they are not as data hungry as traditional AI models. If let's say you can find something that both can do, then quantum computers will have this data and energy advantage. Are there any promising algorithms that promise to do classical neural network? Yes, there are. So this is this reference. So one of the references, this one, this is about traditional computing tasks. So this is, what is that? Yeah. So this is this reference. You can download the presentation in the data. So there are quantum machine learning models that offer or that are already known to offer some advantage over classical models under certain circumstances. But this paper is, let's say, a little bit old. With the advent of new models, you can go and check out the quantum Qiskit neural networks web page to see new references. There, people are exploring more and more models that have some advantages over classical machine learning.
We have one more question. On the note of energy, I heard that quantum computers use an enormous amount of energy in cooling, but consume no energy in the actual chip. Does this mean the amount of energy they consume goes down as the chip gets more powerful?
Sorry, I didn't hear the last part.
Does this mean the amount of energy they consume goes down as the chip gets more powerful?
So first of all, this is architecture dependent. So the cooling is mostly required for superconducting qubits. So there are also optical quantum computers, which they operate at room temperature. They have a different set of problems. So these optical quantum computers, they have problems about single photon detectors. So I don't know what will happen in the future. At the moment, the superconducting qubits with the United States leading the position, they are the most dominant technology at the moment, but China is working very heavily on optical quantum computers. So maybe this energy problem will be not that much of a problem. Europe is very much interested in trapped ions, for example. That is also very energy efficient. Scaling in those systems are a little bit of a problem. They are trying to solve this. From the energy point of view, still in this reference, let's say, oh, it's not going back. Let's see. So if you can go and check this reference on how they calculated IBM Quantum Condor's advantage, you can see that even you are spending so much energy in cooling for tasks that require handling a lot of data, then still quantum computers are much more energy efficient. Okay.
And one more question. Can a problem be distinguished whether it is better solved with classical computing or quantum computing in a practical manner?
It depends on what you mean by practical. The field that studies is called quantum complexity theory. So these are the quantum complexity classes, and these are the classical complexity classes. So if you can go and check these references, you can have an insight on how to, let's say, interpret, how to see if quantum computer will have an advantage over a traditional computer in a particular problem. Yes. Any more questions? Okay, so I hope this introduction was interesting enough for you so that we can see, we can meet with each other tomorrow as well. And tomorrow, let me open the program again. Oh no, it's not this one. So tomorrow I will be talking about Bar-and-Plateau problem, which is a significant problem for quantum machine learning. Some two applications as a scientist I see most advantage in using quantum machine learning for, let's say, tasks in my field. And if we have time left, I want to show you how to use high-performance computers for error mitigation using the MITIC library. So if you are interested in this, please install the MITIC as well. Okay, thank you very much.
I would like to thank our instructor once again for his time and valuable contributions. Hope to see you in the following session that will be held on tomorrow at 9:30 a.m. in Istanbul time. So see you.